Okay, hello. Hopefully, if you got to have some break time last week, hopefully it was good break time. Um, yeah, we're in the last 3 weeks of the semester. For us, 2 weeks before the last project is due. So don't forget the last project is due on December 11. And then, good morning, Magenta. Nice to have you here as always. Thanks for being here. So yeah, the last project's due December 11, and then the week of finals, we will do. Um, we will look at the implementation of some hashing algorithms and then a hash table. But that's kind of bonus material, but it'll be after the last project. All right, so this week, next week, project December 11th, and then one last bit of new material during the week of finals is where we're at. Let me get into our class and let's look at the schedule and the module. So yeah, we're right here. Second week of doing binary search trees. In some ways, binary search trees are easier because they don't have nearly as many operations. Because they are by nature sorted, they keep their data sorted. Binary search trees then don't have the push front, pop front, get front. They don't have the push back, pop back, get back. They have less algorithms. And in some ways, the algorithms are simpler once you get to the point where you understand recursion well. And I realize that's challenging. Most people won't probably in just a month's time or so get to be masters of recursion. That's kind of a lifelong endeavor if you're in this line of work. But it's less code overall because there are fewer algorithms to implement. And the algorithms, because they're recursive, are less code to write themselves. So anyway, that's where we're at. We did binary search trees last week. We will enhance and in fact complete our binary search tree template class this week. It will be fully ready to go. If you complete the lab this week, then you have the binary search tree, which should not need to be touched, added to, altered, or anything else for finishing off project 4. Everything else will be the other parts of project 4. So good morning, Ed Cass. Nice to see you as always as well. Sorry I missed your chat message there. Good morning. Okay, so that's where we're at, and then we'll do hash tables during the last week, kind of as bonus content, but there will be a lab and discussion as always during that last week, but we will have project 4 behind us at that point. Okay, so we'll do it next week, but you need to look at project 4. This would be the time to get all of the command processing part dealt with. It's got different commands, but in some ways it's very similar. So anyway, that would be a thing that you could do. And if you're completing this week's lab, then you've got the data structure part. And then the last part is hooking up the new component, which would be the word class, which we'll implement next week. Okay, so week 15. So we will add some functionality to our binary search tree, a get function, which will retrieve not the data itself, but a pointer to it. And we'll talk about why we're retrieving a pointer to the data and not the data itself in just a moment. We will have a function that confirms the presence or absence of a specific piece of data in our tree. We will print the data in forward and backward order, ascending and descending. And then the hard one, which is removing a node from a binary search tree, which is very, very difficult to do. But what we are going to use the removal algorithm for is a chance to read through a high-level plain language description of an algorithm and watch how we translate the plain language description of an algorithm, the textbook description of an algorithm, into code. So we'll work on that together, although I would encourage you to try anything that I do and show you the answer for. I strongly encourage you to make the time to go back and see how far you get on your own. and then compare it against the answer that we derived in class. Okay, so the reading is a selection from an old textbook that I actually used when I was in school, but I like the way that this person describes the algorithm for removing a node from a binary search tree. So I don't want that. Okay, I'll just come back to this page. In fact, no, I'll just leave that sitting there and I'll open the next page over. So anyway, this is from a textbook, and it is what we will use to derive our remove code from. So we will get the experience of reading a person describing the algorithm in plain language and translate that into code, which is intimidating the first time you do it, actually. So we will do that together. Okay, so the lab, which I've already got loaded into a REPL, it's taking what you did for the tree last week and enhancing it with new functionality this week. So you'll just start, or however it is that you get last week's work in, I retyped it while I was sitting here waiting for the clock to tick over and start this live stream myself, because I always think it never hurts to type it in at the keyboard. But you can do whatever you want for your starting point. And then run the unit test. And then the discussion is another poll, so hopefully that's welcome as you are hopefully spending some time getting your project built for as far as you can build it, waiting for the last piece of content next week. But otherwise, it's just a poll so that I can have some sense of what people find more difficult and less difficult. And then finally, discussion is always Project 4 due on December 11th, which is less than 2 weeks now from when that's due. Okay. So I'm just gonna, let me see, jump in probably. Yeah, so let me touch upon my agenda. So Project 3, everyone's got a score. If you go to the feedback in Canvas for your project, you will have my detailed rubric for your work, so you can see where the points were awarded and where they were deducted, and some at least brief comments about the where and the why of the deduction. So most people's programs crashed somewhere. So if hopefully that makes you feel better. That's typical. I think I had 3 people who didn't crash on it, but no one got the whole everything absolutely perfect, as it turns out, except for me. But I've done it before, many, many times, by the way. So by the time you've done it, 15 or 20 times, you'll probably find yourself quite good at it as well. Anyway, so 3 people got the perfect output, I think, and then we're missing a few other details. But most people crash somewhere on the inputs. All I did was I took a testing file for push front, push back, and a testing file for doing inserts and removes. And I put them all in one file with a clear, destroy, create sequence in the middle of them. So I went through all the push front, push back sequence, and then I wiped out that list in commands in the file, and then did the whole series. So my input was 159 inputs. And all I can say is that's the kind of thing that when you're given the opportunity to exercise your code by simply creating a file of inputs, do that. And try to put sequences of inputs that would expose bugs in your code, which is what I tried to do. But anyway, the one that I built, and I built it manually actually, was 159 lines. So Magenta asks, is the only way to get rid of all the bugs to use a unit test? No. So a unit test, a well-crafted unit test will get you 90+% of your bugs. But there's just always something kind of in a real application dealing with real data that you probably overlooked when you were writing your unit test. So I always assume that I've overlooked things when I wrote a unit test, and that to get the true measure of my code, I'm going to have to run it against testing inputs, like just actually run the application with input data, and then try to craft input data that would expose bugs. Even then, I'm never 1,000% confident that I'm perfect. There's probably always something I overlooked, either in my unit testing and or in my kind of real world inputs that's a bug that I have just overlooked. It's very difficult to root out bugs in software. So that's a very good question. How do we get rid of all those bugs? A unit test to get all the way to sort of what you consider near completion, and then if you have an application where you can feed your code real world data of some sort, like our input files, then that's the next level to do it. And then after that, really you need a new set of eyeballs, is what I would say. So once you think you've got it perfect, then hand it off to another programmer and ask them to break it. And if they have any experience at all, they will probably figure out a way to break your code. But these are kind of the various techniques that we have to try to suss out our bugs. It's quite difficult to do, as you all know. It's hard to eliminate bugs. Okay, so yeah, there's the project 3 thoughts. So on the binary search tree, I know this is very, very difficult. I'm going to draw a picture, which is not going to be super helpful, but these are every function in here in this binary search tree is written recursively. The reason why we do that is because that is way easier, as it turns out, than trying to use loops to descend into the structure of a binary search tree and do work. You absolutely can write algorithms on a binary search tree that aren't recursive, but they are way harder to implement, way harder to implement. And they're not really practical way of going about it. So you want to use this to begin to grow your understanding of and your experience in developing recursive algorithms. They're hard. They take a lot of practice. And this is probably for most of you the first time really that you've practiced it. So it's one of those things, give yourself time. Look for excuses to practice doing recursion. It can be difficult to identify situations where recursion makes sense. For those of you who are going on to a Programming Algorithms 3, you will get more recursion, a lot more recursion in a class like that. I'll try to remember, by the way, let me put it as a note to myself. Another place where you can go to get practice. And I find myself doing a lot of recursion in that place. I'll finish with that. All right, where am I at? Yeah, so recursive algorithms. So I put a little checklist to just try to help in getting used to the pattern. So for a binary search tree, you need to always have in mind whether or not the function is meant to return a value, because if the function is returning a value, then your recursive calls need to return a value, because you're kind of, when you recurse, you are waiting for some other part of the tree to actually give the answer back. So every recursive call is like, well, I can't do it, but I will return what that subtree does. Oh, well, I can't do it, but I will return what that subtree does. And eventually, one of the subtrees says, I got it, I can return, and then it kind of filters its way back through. I'll try to draw a picture of one of these sequences to show you what I mean about waiting for an answer from a subtree. All right, so for a binary search tree, are we returning a value? Because we need to be careful that when we make a recursive call that we return the result of that recursive call. We should usually check for a dead end first. And by a dead end, I mean we are on some link in the tree that is null. That's a dead end, and in many cases, in most cases, that dead end is a place where we can't go any further. In fact, in all cases, it's where we can't go any further. But in the case of insert, we can actually use that as the moment where we attach a node. But for many of these algorithms, that dead end is something went wrong, and I have to stop. We should be, the order can change, but we should ask ourselves, should the left child handle it? Should the right child handle it? Or should myself, meaning the root of the tree, handle it? So let me draw a picture at this point to show you what is in my mind when I'm developing these algorithms. it looks like this. And it's kind of, I would argue that doing a recursive algorithm is a bit of a leap of faith until you can really picture in your head what's about to happen. So this is all, that's one of my best pictures, by the way, of this semester, I think. I guess I can draw clouds. So this is all you can see, as it were, for most binary search tree algorithms. You have some node that you're looking at through a pointer, which our algorithms often call the temporary root. So you're looking at some node, and all you know is that this node has data that I can see, and then whatever is going on down the left child subtree or the right child subtree, I don't know. I don't need to worry about what the structure is down here. If there's a whole bunch of nodes, if there's no nodes, I don't have to worry about any of that. It just is an unknown when I'm developing the algorithm. Same for the right child. Whatever is going on down here in terms of the structure, if there's one node, if there's three, if there's 100, it doesn't really matter when I'm developing the algorithms. I need to be watching to make sure that I'm not here. Because that's bad. All right, so I don't want to be at a dead end. But if I'm looking at a non-dead end, then all I really need to ask myself is my data the data? For whatever the algorithm is my data the data that is required here? If it is, then act. If it's not, then all I really needed to do is say, well, it's not my problem. I'm going to make my left child deal with it if the data is less, or the right child if the data is greater. So this is just kind of me trying to help you practice thinking recursively. The beauty of recursion is that I never have to know the entire structure of the tree. All I really have to know is what's going on in the node that I'm looking at right now. If the node that I'm looking at right now has the data that I want, then I act on it. Whatever the action is, I act. If the data that I have in the node I'm looking at is not the data that I'm interested in, then I either have to pass the buck to my left child, so you deal with the data, or pass the buck to my right child and say, you deal with the data, not my problem. That's it. And then you have to learn that this same picture is what my left child sees. When I pass it down to my left child just thinks, oh, this is the whole world. I don't know what's up here. Doesn't matter. I don't know what's down here. Doesn't matter. Is the data that I want to work with? And if I go down the right child, it's the same thing. We kind of reset our view to be a node with some data and possibly left and right children. And however I got here, I don't know. It's however I got here. All right. So anyway, takes practice. And I'm also, I draw the pictures just to give you some ideas about how you might practice drawing the pictures, because this was the whole trick for me, is drawing the pictures. So let's do one just so you can see an example of what I'm talking about. So this week, which one did I list first? I listed the find algorithm. Okay, so the find algorithm, and we'll try to apply that checklist. Assignment name, 15 lab. I'm doing this. You guys are good about this. No one ever forgets their documentation on the labs in this class. Although sometimes on parts of the project. So if you are working on source code that you type code in, you need to put your name on it. It's like a copyright statement. Anyway, so here I'm copyrighting my work for this lab. So we're going to do the find algorithm. So remember, we have the public interface that really just kind of hides the root pointer of the tree. So let's find. So we are looking to find a target. So I have a note in the agenda about what are appropriate return values. So in most cases, a find, meaning is it there or isn't it there? If we can return a bool on a situation where we either succeeded or failed, that's great, right? Because we can return a true, I did it, I succeeded, or a false, I failed to do the thing that you wanted me to do. That's ideal. So we love it when we can use a bool to signal success or failure. We can't always do that, but in this case we can. So what does it mean to do a find? Well, this is the public version where I'm trying to hide the root pointer from third-party programmers. So I know that internally what I'm going to do is I'm going to call my my private find function and try to find this target starting at the tree's root. So I just want to point out to you, I'm not going to do it. Well, I'm going to do it, but then undo it. That find function, it doesn't care where you start. It's going to just start wherever you tell it to start. So it's either going to start at the very root of the tree, or it may start at some subtree, which is what we do when we recurse. We just tell it, hey, go down to this spot and start there. That's what recursion on a binary search tree is actually doing. So in our case, we're just saying, hey, let's just start at that very root node, and then we will let the algorithm descend as needed. Okay, so I know when I call the private function, I want to start at that very root node, even though technically I didn't have to, but that would be dumb because I'd probably have a bad algorithm. All right, now the private section, the find algorithm. So we'll just use so in this case, now I am using, when I develop this algorithm, I'm not thinking of the whole tree. I'm just thinking of that one node and two unknown subtrees. This t-root is somewhere. All I really know is that I got a node here with data, and it's got possibly children on either side, but I don't care about that. Okay. So we should always, probably first is typical, if I find myself looking at nothing, well, I'm not going to find anything at nothing, so I'm going to return false, which satisfies this function, which also allows the public function to return to my third-party programmer saying, hey, I looked, I couldn't find it, which would be the case if I got to a spot where there's no node. So now I start to ask the questions about, is it my data or is it somebody else's data? So the way I would do this is I'd say, well, and I could do this in any order that I want to. I'm going to do it in the child myself order first. So if the target data is less than the data in the node I'm looking at, so all I know is the data in the node in that picture that I drew, that data is not the data that I want. And since the target is less than that, then I have to pass the buck to the left child. I don't know what's going to happen down there. All I know is it ain't my data. If it's there, it has to be down to the left somewhere. And then I'm being very careful here, because if I just say, I got to find the target and not me, but my, right? So that's my left child tree problem. I'm done. But this is one of those cases where you need to be very, very careful, because I'm making a recursive call on a function that returns something, which means that I have to make sure that the recursive call returns whatever the child produces as a result. Since sort of I, myself, don't have the data, I'm going to have to assume that my left child may be able to find the data. It's also possible that that data is greater than the data I'm looking at, in which case I'm going to have to wait and return the result of making the right child go have a look for it. How is the right child going to do that? I'm not going to worry about it. It's going to do it however it does it. All I have to worry about is what do I do at this one spot? If this one spot's an empty, well, clearly there's nothing. That's a dead end. I got to return false. If the target we're searching for is less than the data of the node that I'm looking at, that one node, then I have no choice but to force it on the left child, somewhere down there, presumably. If the target is greater than the data at that node, then I have no choice but to force it on the right child, whatever that looks like. That's the right child's problem, not mine. There's only one other possibility here. Yeah, right? There is only one other possibility. Well, if there's something here, and then what I want is not less than, and what I want is not greater than, the only other possibility is that it's the exact data. In that case, I can simply say, yep, that's the data. It's here. That's it. Return true. Now I'm going to draw a picture of the get, perhaps. So that's the whole algorithm for the find. When I run it, I get a crash. I'm probably still going to get a crash. Yeah. So I can't run this test successfully yet. Because some of my functions aren't doing what they're supposed to do. Oh, I can see that. So let's do something to get it compiling, shall we? Let's go find the empty functions and stub them out. So here's an empty function. To stub it out, that simply means since I'm returning something, it's going to crash unless I return something. So I'll just stub it by putting a legal return value, even though I know this is not implemented. This one is returning a pointer to something. I can stub it by returning a null pointer, even though I know that's not correct. But I'm trying to just get it to run, if not pass the test, at least not crash. So I'll return a null there. The voids don't need the help. That's a void, doesn't need the help. Insert was already done. Here's the find. I just did that. Here's remove, so stub it. This one doesn't need the help. I like the pointer over there. I think I've decided better. No pointer. Stub that one out. Void doesn't need the help. Void doesn't need the help. All right, let's see if it will run. Still crashes somewhere, which is a bummer. Oh, wait. Let's do the remove main trick since we're working with the template. All right, still get a crash somewhere. Probably in the same place. Let's see where it looks like it passed the one on 27. So what happens after 27 in the tests? Try to find one false. I don't know. Hopefully when I implement some more stuff, it will begin to work. Let's do a quick check just to see. The root's null, the size is 0. Clear on delete. Turn the size. Private clear. Private insert. Ah, there's one right there. I didn't do it. I just did the thing wrong. I'm glad I did it so you can see that. This function promises to find something, but I'm making a call to a private function, and I'm simply going to have to return, yeah, what that function says is what I want to answer. There is a good example. I bet you it doesn't crash anymore, um, simply because I am now actually returning a value in a place where it's supposed to return. Let me try the remove main trick. That's certainly a problem. Still crashes. Although I am passing 9 tests this time. So okay, yeah, now I'm getting a lot further in. So I'm not crashing until I get to line 53 of the unit test. 53. Oh, right. It's interesting because I thought that I did return a null pointer on that, on the gets. Not equal t. Null pointer is not correct. Oh, that's an error. That's not a crash. It crashed later. Probably on whatever's after line 53. That one didn't. It's this one. Aha! There's the catch. It's crashing because it assumes that the get's going to work, and I haven't implemented the get, so it comes back as a null, and crashes if I don't implement that correctly. All right, all is okay in the world. All is okay. It's crashing because I have not implemented the get properly. Okay. So let's do the get. Similar algorithm. At some point I will draw a picture, but I don't know if a picture is going to help, other than to remind you that I am developing the algorithms only thinking that I can see this much. And if I have to do work down here, then I pass the buck by doing a recursive call. Yeah, I'll draw a picture on this one. If I have to pass the buck, then I make a recursive call and I let whatever happens happens. All I have to do is develop my algorithm with this much information. Now the remove is going to break this rule a little bit. But for most of these algorithms, all I need to know is, am I looking at anything? If not, I do whatever I do when I've fallen off. If I'm looking at stuff, then is that the data that I mean to be looking at? If it is, then great. If it's not, then perhaps the data is down here in the left subtree, in which case I just recurse and say, hey, left subtree, your problem. If the data that I want is down the right subtree, then I recurse and just say, hey, right subtree, this is now your problem. And then I hope that the algorithm that I've already developed works for the right subtree and the left subtree the same way that it did for the original subtree where I started. And there's no reason why it shouldn't, because every subtree is a node with 2 children. Every one. Okay. So let's do a get, and maybe this one I will draw a picture after we implement it. No, let's do a get in a picture. Sorry, I'm switching back and forth. Let's do a get in a picture so we can kind of see the function stack. So I'm just going to build a phony tree here. 50, 75, following all the rules. Okay, so there is a legal tree. And if I do a get, I'm going to do it kind of like a stack. So if I say get 30 at root, what's the answer? So if I do a get 30 at root, that's all that I can see. I'm trying to get 30 here. So I asked the question, is there something here? There is. But the data is not right. The data that I'm looking for is actually less than here. So I have to recurse. I have to recurse down to here. So now the algorithm can see this, right? We're waiting for an answer still. Now the algorithm can see this. So the algorithm just says, well, is there something here? There is. But unfortunately, the data is bigger than this. Fair enough. And I'm going to say 25's right, because the data was greater. This is actually 50's left. So still waiting for an answer for my original question, but I couldn't get an answer here, so I had to ask, can you get me the answer? This node said, I can't. I'm going to have to ask if this guy has the answer, which is we're now here. And this guy's still looking at stuff, so that's good, except for the data is bad. So this is 35's left. I'm just labeling the nodes. So that's root, which is really, yeah. And then I go left from that 50. Then I go right from the 25. Then I go left from the 35. But at every stage, my algorithm can only really see this much. Do I have data? Is it the data that I want? Left or right? Do I have data? Is it the data that I want? Left or right? Do I have data? Is it the data that I want? Left or right? So now, do I have data? Is it the data that I want? It is. Yes, it is. And now all those recursive calls that were saying, well, I can't return it, so I'll return what he returns, I'll return what he returns, I'll return what he returns. So finally I got, oh, they said the answer is true. Oh, great. Well, that's going to be my answer as well. That's going to be my answer as well. That's going to be my answer as well, which is ultimately the answer that pops out from that public function. It unravels itself as the algorithm works its way down into the tree, finally realizes, yeah, I've got it. So by the way, if I were looking for 36, the algorithm ultimately would have said, nope, dead end, and then falses would have unraveled them, unwound themselves through this stack of recursive function calls. All right, so that's what we're about to implement. So the get, we will start at the public get, being more careful this time. Okay, so I already have the return, but I can't just return null. What I really need to do is use the private get of the target starting at the root of the whole tree, which is where I should pretty much always start, but technically I don't have to. So I can't answer the question from here, but I'm hoping that I can return an answer by making this function call. All right, now let's do the private get. So I'll go down to the private section, find the get. Here's the get. And then I'll just go through the checklist. So I'm looking at a node or nothing, and then 2 unknown subtrees. I'll check to make sure I'm not looking at nothing. And then I'll explain how the this pointer part works in just a moment. But let's get the algorithm. So I'm trying to get a pointer into the data in a node. But if I find myself looking at nothing, well then somewhere something went wrong. I fell off an end or something, or the tree's empty or whatever. I can't get a pointer to the data that you want because I don't have the data that you want. And then I start looking to pass the buck. Okay, well, can I pass the buck? If we're targeting data that is not my data but less than my data, well, then I'm going to pass the buck. I'll have to wait to return an answer that comes back from the left child. So I'm being careful about the returns here because I have to return the answer that I get from descending into the left subtree. When the target is less, that's what I have to hope for. Now, who knows what happens down there? I could run off on a dead end there. Not my problem. I have a node with data in it and two unknowns. Target, of course, could be bigger than what the data in the node that I have that I'm looking at right this moment is, in which case I'll have to return the answer that I get by passing the buck to the right child. Otherwise, there's only one other possibility here, since I'm not looking at nothing and the data isn't less and the data isn't greater. The node that I am looking at has the actual data. So here's the tricky part, because I don't want to return troot's data, because this is not saying data, it's saying a pointer to data. So I'm going to go show you a picture of how this works. But basically, I don't want to return the data itself. I want to return a pointer to it, which looks like this. Technically, that's its address, but it's a pointer to it. And then I'll switch back over and I will draw a picture of this. So if I have the data in question, I'm going to return a pointer to that data, not just the data. So what does that look like? What does it mean? So I'll go back to this thing. So if I am looking to find this 35, what I'll use my little pencil with the little color on it. So my get. So I want to get a data into this, a pointer into this data. So this thing does not point anywhere until I find the node in question, at which point I return not 35, but a pointer to that data, which is 35. So what's the point of that? Well, the kinds of things I could do with this pointer, there's one bad one and then some good ones. I can use the pointer to re-access the data for viewing purposes. So I'm actually looking inside the node at the actual data in the tree when I'm using this pointer. That is the actual data being stored in the actual node in the actual tree. If I just return the data, then they're just going to get a value 35 back, which is fine for some cases. But for our fourth project, what we actually want to be able to do, since we can now do it, if we have a pointer into this data, we can actually use the pointer to manipulate this data while it remains inside the tree. That can be a good thing because it's kind of like a database. It would allow you to go in and update an entry in a database. The bad thing that could happen here is that someone misuses this pointer and alters the data that we use for sorting purposes. So for example, if I use this pointer to change this data inside the tree to be 100, it would wreak havoc. In this case, that's a where normally we wouldn't trust those other programmers. They're gonna have to be responsible. So I'm giving you a pointer, not to the tree. You can't break the tree, but you can overwrite the data with this pointer, which is potentially a bad thing for the tree. So there's sort of a bit of trust that I will allow you to do that. But you'll see next week that there's a reason why we are extending this trust to share this pointer to the data itself so that the data itself can actually be altered in the tree without changing the tree. So yes, if I change this 35 to be 100, that would be a huge problem. But I'm going to have to allow this bit of trust because we do have some situations where we do want to be able to touch this data and update it in minor ways. So with integers, this is very dangerous. With other kinds of data, potentially dangerous. But we're doing it anyway because we want it for project 4. Okay, so it's a pointer not to the node, not to the tree, but to the data in a node. We can't alter the tree with this pointer because it's only pointing at data in a particular node. But we can alter the data, and that's something that we have to be responsible with. Because if we alter the data in a bad way, we can kind of mess up some of the algorithms. All right. So there's that point. Let's run this and see where we're at. Oh yeah, let me do the get rid of the current main and see if that doesn't help the unit test. Yeah, so it no longer crashes, which is a good thing. Let's see what I'm failing. Zach, yeah, so there's a remove that's causing a size and a find and a get and a print to fail. So that's what's expected because we haven't done the remove yet. Yeah, this one's expected because we don't have a print in reverse order happening. Remove, we haven't implemented, which if, okay, so everything else is related. It runs all the way through now. Everything that's left is related to the 2 remaining functions. One of them I'm going to walk us through, and the other one I will leave for you to implement. Okay, so let me put this back down. And maybe someone in chat, I will just sort of get the answer out there. Let's see. So print reverse order. So that's simply going to be descending order as opposed to ascending order. So this part is print reverse order starting at the root. If we started anywhere else, we would get not the whole tree come out. And then I'm going to go down and just sort of hint at print reverse order. So this algorithm is a little bit different, but it has the same elements. Print reverse and print in order. So here's, I retyped print in order from last week. If we find that we are at a dead end, then we're just completely done. Otherwise, then we kind of have to think, what's the proper way to go about that unknown left child and that unknown right child and the data myself? Sorry, there's a moth in the room, which is why I was waving my hands. I like this on there. Okay, so if I'm looking at a node and I want to print everything in order, well, the way to achieve that is to make sure that my left child has gotten to print itself in order, because everything there would be less than me. Then I print the data that I'm looking at, and then I print everything that's greater than me. How the left child does that is the left child's problem. How the right child does that is the right child's problem. As it turns out that if this algorithm is correct, the left children and the right children are no different than their parent node, which is they also have to wait for everything less than them to print, then print themselves, then wait for everything greater than them to print. And then everywhere where we hit dead ends, we just do nothing. So we only do any of this if we're not presently at a dead end. And then all the dead ends just kind of do nothing. Okay. Notice, by the way, I'm not doing a return here. And the reason I'm not doing a return is because the function doesn't return anything. So it's safe to do a recursive call on a void function. There is nothing to return back down the stack, so I don't. So the one thing I'm going to point out to you is that reverse order is the same. except for in reverse. It's right, center, left. And I'll just leave it at that. Reverse order is right, center, left. It's the same algorithm, the same check for dead ends, except for we go right, center, left. Be careful that your recursive calls are recursing not to print in order, but print reverse order. So we got to do everybody in reverse all the way down. So this thing is very similar to print in order. The null check recursing to the right to get in reverse, center recursing to the left. Okay, now let's do remove, and that's the scary one. So the first thing we're going to do is go to the public section, and we will go to the remove function, and we're going to return false here. We're going to return a call to removing the target starting at the root. So here again, I don't know when I write this line of code right here what the result will be. All I know is I can't answer the question about whether or not I can remove that target until I have allowed this function to answer back about whether or not it did. So I will return what this guy does, and then leave it at that. Okay, so we'll go to the private section and then do the scary thing. So I'm going to be doing a little bit of tab switching here, and I'll try to hopefully not do it so often that it causes anybody seasickness, but we are going to use this document. So it's the same document you can see. We're going to use it. And I'm just going to show you where I have made adjustments to match my function interface. So I can't highlight anything, unfortunately. Okay. But leading into this section in this textbook, it tells me I'm going to need two functions. A remove function that returns a bool, takes a pointer by reference to some subtree, and then some target data. So let's go see about matching up our remove function to this subtree pointer, subtree root by reference, and a target piece of data. So the one thing we did different, which it doesn't really matter, but here's our version of that remove function. The important part is that we have a pointer by reference to a node, which is a root of a subtree. And then we didn't do the const ampersand target thing here. We could have, but we didn't. So it's fine. And we're just given some target that we will look for. So here is how I adapted the textbook to my code. I have a target, which is a templated type T. I have a reference to a pointer to a node. I return true or false. For the most part, it matches. But I did need to make some changes. Now, it's also telling me right off the bat that I need a void returning function called remove max. Takes a pointer reference and a reference to the thing being removed. So here's my remove max. It's a void returning function. Takes a reference to whatever that thing is being removed and a reference to a pointer. So that's how I translated the textbook function headers into my code. It's a little bit scary. I had to sort of make note of the fact that he's using the word item where I use T. And then he has a little bit more verbose function naming strategy than I do. But notice this item is what T is. And then notice here also item is what T is. The things I was most careful about is instead of a const reference, I just did a T target, which should be fine. And I did do the pointer by reference. And then the second one, I did do this reference to a thing being removed and then a pointer reference. Okay. And then it says, so this would be, if you picked up this textbook, and we were sitting there together working on it, we'd read this together, which is I'm going to read it to you, and then we would just kind of see if we can implement what it says. So you will need to implement these two functions at the top of your implementation file, which I didn't call mine bag6.template. Okay, so I am doing in the process of implementing both of those functions. Their purpose, I do not know yet, other than it just says you need these two, and I had to translate them into my setup. Okay, and I'm going to have to keep track a little bit of the way that I translated things, because notice where he says root underscore PTR, I say troot. Things like that I will be careful about. Okay, the only purpose of these functions is for your use, making the removal easier. Since you don't intend for other programmers to use these functions, that's exactly what we did. We made them private. There is no need to mention them in your header file, i.e. they're private functions. They are not for any but internal use. Okay, with them in place, then the public remove function, which is what this little paragraph is talking about, can do its work. Here we go. How do you do the remove function? Has a recursive implementation. Got it. Here are the cases, meaning decision tree. The binary search tree could be empty, indicated by a root pointer that is null. If there's nothing in the tree, there's nothing to remove, and the function returns with no work. So right here, what does that look like? If the root I have been given, which I call troot, is null, there is nothing I can do. I cannot remove a thing from an empty tree, so I don't do work, I just return false. That is the end of the road. So notice that this algorithm from the textbook does the same thing that we like to do, which is to deal with that null pointer right off the bat if possible. All right, so that's the first case from that reading. Could be empty, indicated by a root pointer that is null. That's just what we did. 2, could be non-empty, with the target data less than the root. In this case, make a recursive call to delete from the left subtree. We already know what that means. Pass the buck. So else, if the target data is less than the data at this node that I can see, then all I can do is say, not my problem. I will wait for an answer to come back from the left child. We love it when that happens in a recursive algorithm, when the recursion has to deal with the problem. So all I have to do is make sure that I return whatever answer I get from descending the tree. So case 2 was easy. There's some extra text here. This works because the left is the root pointer for a smaller binary search tree. That's the idea, right? So we just go down to that next tree, and then we assume that the view is a node with data and unknown subtrees. Okay, that's case 2. Case 3, the tree could be non-empty, already there, with the root entry less than the target. In other words, the target's greater than the root. So the way he says it is else if the data here is less than the target data. But I'm going to keep going with the way we've been writing it, which is the target is greater than the root data. Then what we have to do is return the answer we get by passing the buck down to the right child. So far we like this. This does not seem that bad at all. Surely there's something that has a removal involved. Case 4. The tree could be non-empty with the target equal to the root entry. I know what that looks like. That's the only other possibility here. That's the only other possibility. Case 4. Turns out that case 4 has some subcases to it. So the tree is non-empty and the target is equal to the root. That we know. Hey, we found the data. So we need to get it out of there. And it says, but be careful, we can't simply delete this node because it may be in the middle of a bunch of other stuff, and deleting a node in the middle of other stuff would be a monster problem. So in this example that you can see the picture, if I were to remove Seattle just by deleting it, then everything that comes below Seattle would disappear, and that's a giant bug. So we can't just say delete it and be done. So what do we do? Well, we have, it tells us here that, and we have two separate situations. The root node has no left child. Okay, so if the root node has no left child, so notice here, this is, we haven't done this before. We've gone kind of poking around, where we're actually looking, we're taking a peek down at the left. We're not just letting recursion handle it. This algorithm says, go ahead and have a peek, see if there's anything there. That's 4A. The root node has no left child. The root node does have a left child. Well, that would be the only other possibility. So here's where the action looks like it's probably about to start happening. I take a peek. Is there somebody down there? If there's not, something's going to happen. If there is, something else is going to happen. All right. So 4A. The root node has no left child. I do not, by the way, like the pictures that this text offers, but if you like them, I just can't as quickly put the strings in alphabetical order as I can put numbers in order to see how this works. So I'm going to ignore the picture and I'm going to ignore the text that says, for example, you might be doing this stuff. All right, that's fine, but just tell me how to do it. So, okay, whatever 4A is, that's the if no left child. In this case, we can delete the root entry and make the right child the new root node. Okay, so now we got to do some translating. We got to do these three things. Old root pointer equals root pointer. So this is a thing to keep track of. There presently is nothing called old root in even the textbook code. Nothing. So I'm going to have to create that. There is something called root pointer, which is this thing right here, which I can't highlight in this reader, but what he calls root underscore PTIR, I call troot. So scrolling back down, old root, I'm going to have to create that. And then root underscore pointer, that's troot. So we're going to have to create old root and set it equal to troot what? What was it? Troot. Okay. So some of the challenges when you are translating textbook code into your own function program, your API, if you change the names of things, then you kind of have to keep track of, what did I call root pointer again? I called it troot. What did I call old root pointer again? I didn't. What did he call old root pointer? He didn't. Oh, that means I got to create something for that. Fair enough. All right, so everywhere root underscore PTR is my troot, so then I will say troot equals troot, right? And then delete old root, which I called old root. And then anything else that I need to do. So I need to reduce the size by 1 because I just deleted a node. So just being careful about that. That's all he says. So let's do a picture of this and see what just happened. I can use the same tree, but I made a mess of it. So 50, 25, 75, 35, 30. 50. 25. 75. 35. 30. Okay, so the situation that we just dealt with, come on. Focus. Why won't it focus? Well, it should. It's not. There we go. Finally. Stupid camera. Okay, so the situation that we just did is we're trying to delete a node with no left child. So all I'm going to do in my little example here is look for a node with no left child, but that has right children because that seems interesting. So here's one. So if we were to delete 25, what would that look like? Well, we'd start the process here and we'd discover, oh, that the data I want to delete is less than this. So we'd return a recursive call to delete left child. So what's important is that we are actually passing by reference these internal linkages in the tree. In code, I'll switch over. In code, that's what this star ampersand means, is a link that's internal to the tree. So when we recurse, we are actually passing a link that is internal to the tree right here. And then we say, is it null? Nope. Is the data less? Nope. Is the data greater? Nope. That's the data for A, because if there is no left, then what happens? Well, we take a pointer to it and we call it old root. And then we take troot, the internal one, troot, and we say troot equals the thing to the right. So we literally move this to point here. What else did we do? That was it. That was what we did. We moved that there, and then we deleted old root, which scrubs all of this stuff out. Let's see if I got a piece of note card. So we end up with a tree that looks like this. Notice that it still follows the rules correctly. So that's what we just did, which is pretty darn cool. Okay. We have to redraw that picture when we come back to it. So that's the part we just did, part 4A, which was this sequence right here. 4B, let's go see what it says. Here we go, 4B. In this case, the root node does have a left child, already established, that's the else part. So we can't simply move the root pointer around because we'll break something. We could do some checking stuff, move the root pointer left and some other stuff. Find some, anyway, blah, 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 blah. But, there's a but. And then picture, I don't like the picture, so I'm going to glance over that part. The plan, picture, All right, so finally, if we read through all this junk where it's describing how should we do, what should we do, we finally get to what should we actually do, which in my opinion, I'm going to do it, and then I'm going to go figure out what it did, is how I work these problems. So finally we get down to, so how do we delete the largest item from the left subtree and place the same root? Okay, so we're going to do something. Anyway, we're going to use our remove max function. Here's the call. We're going to remove max on the left child with the data. Okay, mine is a little bit different, but basically this else part is we are going to remove max. I'll use a this on it just because I want to remember it's internal. We're going to pass the... oh no, we're not passing the target, did you notice? We're passing the root's own data. And the left child, right? Correct. Let's go back and double check. The root's own data, not the target. And then the root's left child. So the root's own data and the left child from this remove max function. So now we got to go down and do this remove max. I should note, by the way, in case 4A, that's a success. Case 4B doesn't return from that function, so I'm just going to have to manually do the work of reducing the size by 1 and returning true, because I know I found it. It's a problem of getting it out of there. So I can easily get it out of there, or it is more difficult to get it out of there. Okay. Yeah. So let's go figure out remove max. This thing. Remove max. Remove max function remains to be implemented. We'll leave that as an exercise in recursive thinking. Now the author says that, but then the author goes on to tell us what to do. So isn't that wonderful? Two cases. The base case occurs if there's no right child. I know what that means. Down here in remove max, if there is no right child, in this case, the largest item is at the root, whatever that means. So I can set removed. So here again, it says I set removed equal to the data from the root, move the root pointer down to the left, and delete the root node. So I have to be careful when I am translating this. What is removed? So if I look at his API way up here on remove max, removed is actually the reference parameter. So I need to be careful that I am using my own reference parameter when he talks about here in number 1, remove. Set removed equal to the data from the root. So where is it? Here we are. So my reference parameter is also called removed, and he says to set removed equal to the root's own data. Okay. Set removed equal to the data from the root. Done. Move the root pointer down to the left and delete the root. So he doesn't tell you all the stuff that you need to do there. But if I move the root down to the left, well, that makes no dang sense. Because if I move it down to the left and then delete it, maybe, I don't know, it just feels like that may not be in the right order. So what I'm inclined to do is say, well, I can't just move it and then delete it to the left. That doesn't make any sense to me. So what I'm going to do, move the root pointer down to the left and delete the root node. So I'm going to assume that it's something similar to what we did before, which is old root equals root. Then I'm going to move it. Then I'm going to delete what it used to be. And we'll draw a picture and see if that works out before we call it good. And I think that's all he says. Yep. So number 2, on the other hand, meaning there is a right child. That is the else part. There is a right child. On the other hand, if there is a right child, there are larger items, in this case, recurse, to delete the largest item from the right subtree. So I'm all right with that. I just say this, remove max, what we're removing from the right subtree. I don't need to return anything from remove max because it's a void returning function. Which is why up here in the regular remove function, I had to manually deal with size and return true. I'm going to refactor this to make it cleaner in a moment too. But let's just see if this works. Let's see what it does. So this is my approach anyway, as I carefully follow the instructions to the best of my ability. And then I go draw a picture and see what it did. So this time there's a right child. So this time, 50, 75. Come on, thing. I guess I'll just keep going and it will eventually catch up to me. 35, 30. And we're putting a right subtree this time. And why not make it hard? less than 20, but greater than 20. Let's put 21 right in here. All right, so the picture's getting messy, but let's just see what the algorithm does. So remove 25, which has a left subtree, which triggers this whole thing. So we start here. Well, that's not that. All right, so here's my target data, 25, and it has a left child. So what happens in the algorithm? So we remove max. So let me get remove max in view. So now it says, and I did this on purpose, at least I was hoping to get it to do this on purpose. Wait, can you see? You can. It says, if the right child is null, so it has a left child. If the right child is null, it's not. So I have to recurse. So here I'm being careful because I need to remember that this is removed. It's a reference, and I drew it in blue because the reference means that we're actually going to be doing something to the data while it still is inside the tree. We're not taking it out. So we're doing something with this data by reference. This is why we have the ampersand removed inside the tree. Crazy. Okay, so we're going to recurse down the right. So we come back in. Removed is still here, is still blue, the 25. So this time we're on the 35. So this is still removed, but we are now here trying to do something to this. So we came to the right. Now we're looking at 35. And the algorithm says, if I have no right child, okay, so I'm there. Removed equals troot data. So I have no right child. So what it's saying is take this data and actually overwrite this location with 35. So at the moment, I'm actually taking the data from here, the right child, who has no right child, and I am just overwriting the data in the tree to be a 35 right here. Now what happens? I put a pointer to that 35. Hold root. So got that. Where you have troot here. And then I say troot equals troot left. So troot equals troot left. Delete troot. And I'm going to redraw the tree, but then the algorithm's done. So notice the trick that he did is he never actually deleted the node in question that had the original data. He descended into the tree, found the largest piece of data down here, and moved it up. Now, why did he do that? That's because that's the only way to ensure that the ordering of all the data remains the same. Now, the resultant tree that we get, I'm going to draw it smaller. We get a 50, we get a 35 here. We get a 20 out here with a 21. And then we get a 30 right here. So pretty dang clever. He actually he went down in here, found the largest piece of data, copied it up, and then deleted the thing that had the largest piece of data down here, which magically removes that data by overriding its, and then removes another node that contained that data so that all the tree still retains its proper associations. Everything to the left of 35 is less than, everything to the right of 35. That's wrong. So that feels wrong. Did I read it wrong? Troot left. Unless I drew the tree wrong the first time. I didn't. So something's wrong. I'm unhappy. Unless I put the 30 in the wrong place. Yeah, that 30 less than, that 30 can't be there. T root right equals null. I'm going to go back to my original tree and let's see what we did wrong. T root right. Okay, so let's put the 25 back. So we have to recurse. We're here. T root right equals null. Then we could do all this stuff. That feels wrong. We'll have to try it out with the test. It feels wrong. Maybe I read something wrong. Move the root pointer down to the left. Is that what I did? Move the root pointer down to the left and delete the root node. Move the root pointer down to the left. And delete the root. Did I read it wrong? No right child. In this case, the large item is at the root. Yes. Anyway, feels funny. I'm about to unit test it, and we will find out where I possibly made a mistake or not. Let's try it. Let me do the, if it doesn't seem to, I would just recommend that you do this step because the template doesn't necessarily cause Replit to recompile everything. So just remove the executable and then rerun it. Yeah, I felt like something is not right. Oh, I haven't done the prints. Oh, but it seems to be working. So I messed up somewhere in drawing this picture. 35. Oh, wait. Let me think. Anyway, it works, which is disturbing because I talked about it differently than what it worked. That's what it is. I drew it wrong. Let's redraw it. All right, this will be where we can stop for the day. Because it's correct, I just drew a bad picture. But we want to get all those things correct. So there's the 25. There's a 35 and a 30. So here's where I went wrong. Is that it goes to the left. I sent it to the right from here. It goes to the left from the main remove function. It first goes left, then the remove max function does stuff to the right. So I got a step ahead of myself. So we end up T-root down here instead. And then what this one does is, as long as there's a way to, we go down to the left and then we go down to the right. So now we start going to the right. We end up here. So what would have ended up happening is we actually would have taken the 21 and copied it up here. So we go left once and then we go all rights for that remove max. 21, and then we would have deleted this one, and that would have been the end of it. So it makes more sense. Well, it has to work this way. 21. Has to work that way for it all to work. So what I wanted you to see is a process kind of going through a textbook. Yeah, so you're right, Magenta. Magenta asks, so it goes left once. What happens here? It has to go all the way right until there's no more right to go to get the largest thing down here. That's correct. So, yeah, this algorithm will keep recursing until there's a dead end, at which point it will take that data, copy it up, and then delete the dead end. And then move everything that happened to be down here up. So you're exactly right. I just drew the first picture wrong. But anyway, the whole process, mapping it onto your API, meaning the way you wrote your functions and named your variables, then sort of reading the plain language description and getting sort of the cases with if statements, and then making sure that you are constantly aware of how you map the names in the textbook description to the names that you chose in your own code. And then finally, drawing pictures to actually try the algorithm out to see that it works or not. So the first time I did it, I realized something's wrong. Either I did the algorithm wrong or I understood it wrong and drew the wrong picture. So I drew a new picture and went and restudied the algorithm again and discovered that I had glossed over what the algorithm correctly did, which is go left once and then go right recursively until it can find a value to copy up. So, and then I finally drew the final result of the tree so that I could double check to make sure that all the relationships are correct. So anything to the left of something has to be less than it. Everything to the right of something has to be greater than it. So that passes all of the unit tests except for I did not implement print reverse order, which I'm going to leave for you guys to do. Otherwise, the main point of this was to let you watch me work through this textbook algorithm. You have the textbook pages. There's just like 3 or 4 of them where you can go through this process again if you want to, or at least kind of sit there with the words and sit there with the code and see if you can make sense of how I got my solution. And it does unit test at least correctly. It's failing where print reverse order is not present. One other thing, and then we will call it a day. This right here, this else part has duplicate code in it. I am doing this size minus minus and return true twice. It turns out that no matter which of these mechanisms I use to delete a node from the tree, if I get into this else part, I'm deleting something. So I can get rid of the duplicate code by making the this size minus minus and the return true be part of the else, and then I don't have to have them be part of what specific mechanism I used to achieve the removal. So one of 2 ways to get the node out of there, and then either way a node's gone, and I will reduce the size by 1 and return true, which reduces the amount of duplicate code I have to read, which is less confusing. Oops, sorry. Thank you, Magenta. You were looking at the I was making you look at my drawing, so let me redo all that. Okay, so what I just did, what I was just working on is this else part. I have this code twice. And what I realize is I don't need to do this size minus minus and this return true twice if I'm clever, because really this else part is a successful removal. And the if and the else parts inside of it are just the 2 different ways the removal is achieved. So I can take the else part and do the size down thing and the return true thing, and then I'm going to remove the duplicates. So whatever mechanism I use to achieve the removal, I downsize and return true only the 1 time. And I let whichever of the 2 deletion mechanisms do their thing. You're seeing that now, aren't you? Yes, you are. Okay, so that's the removal. It is based on that few pages of textbook that I supplied in your readings this week. Everything is here but print reverse in order, which is very much like print in order. Just be careful that when you recurse, you are recursing to print reverse in order. because the recursion, the reverse recursion needs to be all reverse recursion. Okay, that's it. I'm going to click run. Actually, I need to remove main. Oops. So removing main just guarantees that the compiler is going to pick up your altered template code. And then everything that I'm failing is the print reverse in order stuff. And I can see that because I can see things being printed reverse in order, and I know I didn't even implement it, so nothing should happen. Okay, that is it for me for this week. So please do go look at Project 4. You can start it. You can build the infrastructure for the command processing, or at least most of it. You have, after this lab, the complete binary search tree. So you can add that to your Project 4, even though it's not ready for prime time because you don't have the data to go inside the nodes yet. We're implementing that next week. But you can have most of the command processing ready to go. You can have the binary search tree after you finish this lab and unit test it plugged in for your project. And then the last thing will be that we're doing something a little bit more interesting than just integers inside of the nodes this time. Okay, I'm going to cut out with that. Have a great week. Thanks for being here. Thanks for having my back, Magenta, and reminding me I need to get the code back up for you to look at. So Canvas Inbox, Piazza, office hours, as always, back to normal routine this week. Next week, we will add the last piece, but you can build out a lot of sort of the just the brute force work of getting all the command processing set up and ready to go so that we can start plugging stuff into it. That would be a good thing to do between this week and next week. That way you can drop in what we do in lab next week and you're pretty much done with the fourth project. Okay, have a great week. I'll see you on Monday next week.